Hi there, welcome to this lecture series on matrix algebra. This is lecture 22, part 2. This is the second lecture on the topics of eigenvalues and eigenvector. In this part of the lecture, we'll go through coordinate changes and in particular using eigenvectors as basis of the new coordinate. Let's get started. So in part 1 of the lecture, we went through the statement of a theorem, and then we took an example in the two-dimensional space to verify. In this part of the lecture, we'll go through a proof for the theorem. So let's state the theorem more precisely. So it says that if now I have a basis of a vector space Rn or Cn, with the basis with the vectors v1, v2, and vn, and these are eigenvalues of the matrix A. Then, by choosing a matrix, let's call it P, which takes all these eigenvectors as its column vector, so P is a square matrix, and then we can obtain a diagonal matrix from A by making this multiplication, that is, P inverse times A times P will be a diagonal matrix. And in particular, let's say the diagonal elements are lambda 1, lambda 2 to lambda n, then they are corresponding eigenvalues of the matrix A that corresponds to the eigenvectors in the corresponding positions. Okay. So towards the proof, let's first take a preliminary computation. Now, if you multiply a diagonal matrix with just a normal matrix, let's say the diagonal elements are lambda 1, lambda 2, so on, all the way to lambda n. So what happens to the product? Well, the product is the following. You can just carry this out by computation of the matrix multiples. So you know that this one cross that one, the inner product will give you this element, and then you see it's just lambda 1 times b11, and you can easily verify that in the first row here of the product, all the elements are multiplied by lambda 1, and they're taken from this matrix. Let's call this B. And then the similar thing happened to the second row, which will be just taking the second row here and multiply everybody by the lambda 2. And so on and so forth, all the way to the last row, which will be this vector here multiplied by the lambda n. Okay? You can verify by definition of the matrix product. And then similarly, if we switch the order of the multiplication, let's say we have a B matrix here, multiplied by a diagonal matrix, lambda 1, lambda 2 to lambda n on the diagonal. What happens to the product? Well, it's very similar to the previous one, except that now it's kind of the effect of this multiplication of lambdas will be like kind of a transposed. So you will see that the first column here is this first column multiplied by lambda 1. And the second column is the second column in B multiplied by lambda 2. And all the way to the last column is the last column in B multiplied by lambda n. Okay, so this we will use in our proof. Okay, now let's look at the details of the proof. So we are assuming that v1, v2, vn, they are linearly independent eigenvectors of A, corresponds to the eigenvalues lambda 1, lambda 2 to lambda n. And then we form the matrix P by taking these linearly independent set of vectors, and therefore the P is invertible. Okay, so let's look at A times P. What does that equal to? And we can perform a matrix multiplication by columns. So P is just these column vectors. Then A times P will be A times this matrix here formed by these column vectors. And then we see that the product can be written as A times each vector. It will fill the corresponding column in the product. So the first column here will be A times V1, and the second column here is A times V2, and the last will be A times Vn. And now we use the fact that these V1, V2, Vn's are eigenvectors of A, corresponding to the eigenvalue lambda 1, lambda 2, lambda n. So in particular, A times V1 would be lambda 1 times V1, A times V2, lambda 2 times V2, and A times Vn will be lambda n times Vn. So we see that we are multiplying each column I is multiplied by a lambda I. So recall the preliminary computation we did on the previous page. So all these lambdas you can take out and form a diagonal matrix, and multiplying on this matrix here on the right. Okay, so we see that this is P and this is D, so we write it down. So what we have proved so far is that A times P equals P times D, which we write here. So you can multiply this equality on both sides. On the left, multiply by P inverse. Then the left-hand side becomes P inverse times A times P. And the right-hand side, you have a P inverse times P, which is identity. Then you just get D. And then you get that. Okay, so that's exactly the statement of the theorem, so we proved it. So this leads to the introduction of a concept we call similar matrices. So here's the definition. If you have two m by m matrices, let's call it A and B, we say that they are similar if there exists an invertible matrix P such that this relation holds. So B would equal to P inverse times A times P. So now let's recall our discussion on coordinate changes. So we recognize that this definition here states the following. Two matrices are similar if they represent actually the same linear transformation, but with respect to two different sets of coordinates. Okay, so if now you have a coordinate x and then you have a y coordinate, and they are related by x equal py, and then the transformation by multiplication of matrix A times x in the y coordinate would be represented by this matrix B. Okay, so that basically says that if two matrices are similar, they are more or less describing the same linear transformation. Okay, so this similarity actually also leads to a thing called an equivalence relation. So here are some properties. So first, a matrix A is similar to itself. So you can easily verify by seeing that A is the inverse of the identity times A times the identity. So take that P to be the identity matrix and you easily have the relation. And then if A is similar to B, then B is similar to A. So it's symmetric. So this says that B equal to P inverse times A times P would imply A equal to P times B times P inverse. And this you can easily verify by multiply P on the left of this equation. Then you get P times B, and then P and the P inverse makes the identity. So you can drop that. And then you multiply with P inverse on the right. Then you get a P inverse here, and then you get P times P inverse on the right, which is an identity. Then you get A equal P times B times P inverse. And the third property is that if A is similar to B and B is similar to C, then A is similar to C. Now let's verify this statement. So the assumption is A is similar to B. That means there is a P matrix. We can write them like that. And then B is similar to C. Then that means there is another matrix. Let's call it Q. And we have this relationship. So what we can do here is, for this B here, we'll plug in this relationship here. So we'll have C equal to Q inverse times B, which is now this complicated term, and times Q. And then we can group them. We can do the Q inverse times P inverse and do that product first. And then we recognize that that product is the P times Q inverse of the product, but in the reversed order. And then P times Q, we group it. Then we see that C satisfies this relationship, which means A and C are similar, where the matrix here, P times Q, is the one that we would standardly use. We call it as P. Okay, now this leads to an important procedure in matrix algebra that we'll see later on. It will be very useful, important. That is to diagonalize a square matrix. So here is a theorem. It says that if a matrix A is similar to a diagonal matrix, then that statement is equivalent. So if and only if one can find a basis, V1, V2, Vn, of consisting of eigenvectors of matrix A. So meaning that the matrix A will have a set of eigenvectors that are linearly independent. Then you can diagonalize this matrix. So and the proof, well, it's a straightforward proof of, just follow from what we have talked so far. So we can choose this P matrix. We form it as a matrix using all the eigenvectors like that. And then we can do this computation. And then we find out that it exactly equal to the diagonal matrix D, which consists of all the eigenvalues along the diagonals. Okay, so that is just a straightforward proof. Okay, so we have reached the end of this lecture. In the next lecture, we'll follow up on the discussion of diagonalizing a matrix and talk about many more details on that. Okay, so I hope you enjoy this lecture, and I will see you next time.